Okay, so let us see how this equation come uh, is formed. So, uh, so as you can already know the spring mass system. So let's say we have a spring mass. This is our fixed support, and then this is a spring. Okay, it should be homogeneous, and then attach with one mass here. Okay, so we have the spring coefficient of the spring. Spring constant is denoted by K. So usually it's Newton per meter, and then this is mass. Okay, this is mass. So this is mass M, and then let's say this is in equilibrium stage. Okay, so it's at the equilibrium stage here. Okay, so if this one is at the equilibrium state like this, so if we break this one, if we break this system into a different force, we will get it like two force, right? So this is, we have Fg, this is force by gravity, and this is another one is the force of the spring itself, correct? Right? So this is let us say this is Fs. Okay. All right. So this is two system, and let's say we take the direction of positive is downward according to the spring extension. Okay. So uh, we will have Fg, correct? Fg plus Fg is equal to Fs according to second law of the Newton, right? Okay, and then if this is a system, we add one more, uh, we add one more, we add the dumping system, dumping like a dashboard. Okay, dashboard. We add one more force actually. We add one more force. For example, let's say this is a dashboard like this. Okay, this dashboard have the constant. This is a dumping. This is a dump. So this is a dump, which is represented by dashboard, and then this dumping, this dashboard have a dumping constant. Let's say C. So you can see that this is C. We have the another force when you strike like this, and then if this system is disconnect from this spring, so now this one will move up like this, right? So meaning that the force will be go up like this. Okay, so this is let's we said this is for the dam is SP. Okay, so the SP, so now we can see that we have three now. Okay, so this is already uh, equilibrium. So if we add one more force, so here will be SP, we add one more force. Okay, look at this one. So we will get, if we make it in the magnitude, we will get uh, Fg is equal to minus, right, Fs minus Ap. Okay, so we have Fg. So Fg is the gravity force. So gravity force is equal to mass multiplied with the acceleration. So let's say, okay, so this is uh, okay, so support, fixed support, and this is our spring. Okay, before connect to the mass, so it will be at this level. So now this is the y. Okay, so this g equal to y m multiply with the acceleration. Okay, mass multiply with the acceleration, and then we have uh, Fs, which is a force induced by spring. It will equal to spring mean K, sorry, is K multiply with the uh, uh, K multiply with the acceleration. We have speed. Okay, K multiply with the speed, and then we have Fp, which is the damping. So it will be equal to the damping constant multiplied with the y. Okay, okay, damping is multiplied with y. Okay, so all of these are equilibrium. Okay, so meaning that we attach the string, attach this one, and attach this dashboard. This is the dashboard representing the damp, and then we attach and then let them rest at the equilibrium stage. So we will have this equation, right, based on the Newton law. Then this one will be equal to mass with the acceleration. This one will be equal to the spring constant multiplied with the speed, and then this damping, I mean this one will be equal to the damping constant multiplied with uh, the length. Okay, so that's why we will get Fg. So we have mass multiplied with the acceleration equal to minus Fs. So we have K y dash speed minus c cy a cy. Okay, so you can see from here, so we get m y dash here plus c y dash plus k y dash equal to 0. Okay, so this is the equation coming from this system. And then okay, so as yt is a function of time, so meaning that now we would like to observe no, we would like to observe keep, I mean, if this we try to observe, you know, because you can imagine you strike this one, and then you remove this damping item, and then let the mass and the string move. Okay, so you can see that the graph will be something like this, right? So So this is y, so this is y, and then this is time. So this is time. So you can see that um, if we change, if meaning that, so let's say we start uh, our this one in, let's say here high, okay, it's very long. So now it's long, so it could be something like this, okay, long, long, time one, and then a little bit short, time two, move to, you can see this one start here and then go to there. You see, it's long here, and after that minus. It could be minus here. So this could be plus, and this could be minus. So long minus string go in, and then after that go down, slow lower, and then after that go up again minus. Okay, but short now, and up till it go to the equilibrium stage. All right. So that's the actually this is the equation. This is the equation uh, represents this graph. So this is what we try to observe. Okay, so here yt is as a function of time. T is the displacement of the body of the mass m from rest, force within the system, initial y dash double dash, and that was c dash if c greater than 0, and the spring force ky acts restoring force. Okay, so the corresponding characteristic again. So from what we learned before, we can apply here. We can apply here from the equation. Okay, from this equation, and then from what we learned from the previous regarding the second order ODE, so we can find the solution for the here. Okay, lambda here, and then lambda is the quadratic is a solution from this quadratic equation, and then we have okay, we have two, actually three cases. So we have the, if the solution of the equation have two, so this is, we call it overdamping. If the solution is one solution only, this is, okay, this is double root, double root, so this is a critical damping. And if c square is less than 4 mk, so this is under the damping. Okay, so this is what I tried to explain to you. You can see here, this is the critical damp. This is under damp. This is over damp. Okay, case one. This is case one. So when the damping constant C is so large, greater than 4 mk, okay, this is real good in general solution is like this. And if damping under damping means it's less than that, that's the conjugate solution, meaning that this is the imaginary solution. Okay, and then we have critical damping when c square is equal to 4 mk. So this is the solution for the critical damping. And then undamped system. So let's say we don't have, if the dam is, or the system is so small and that can be disregarded, then from this equation you can see, from this schematic diagram, okay, so if this damping system, this damping force is small, so we connect it, so it become, so it become like this. Okay, so general solution of this, so y equal to goes I don't know, this is okay, so is equal to this result. Okay, so this is the result. Okay, so we will go to the example 2 after next while.